Welcome back, folks. In this video, we'll be talking about vectors part 2. In this video, we'll cover resolving vectors into components, adding vectors using components, and smart and dumb pilots in boats and airplanes. Okay, first of all, any vector, in this case vector A, we can break that vector into two individual components, both in both the horizontal and vertical directions. Okay, so if we write that as a vector addition, vector components just make up the parts of what a vector, in this case A, would be. Okay, here's another way to draw it. AX, if we think of drawing AX plus AY head to tail like we did with vector addition, AX and AY are just components of an individual vector. Okay, so resolving vectors into components, here's some notes where it's just, really we're just breaking vectors into both horizontal and vertical parts. If we go over and have a look at what this looks like in this PhET applet, if we look at just this vector D, this vector D at the top, it even tells us our dx and dy, those are just the components. Over at the side here, we can click on a couple of these different buttons to show what those vector components will look like. So use this PhET applet to reference questions that you're doing to double check things and just make sure what you're doing is making sense. Okay, so when we are resolving vectors into components, we're just breaking them into horizontal and vertical parts. So here's an example where we're asked to find the horizontal and vertical components of this force. This would be the force of pulling, a kid on a sled. Okay, the other question that just popped up there by accident is just, we'll get to that one next. Okay, so if I back this up a minute and look at both the horizontal and vertical components of this force, I'm just going to take this 60 Newton force and I'm going to draw on it Fx and Fy. The magnitude or size of this thing would be 60 Newtons. Okay, so to go and then do some math to find out what Fx and Fy would be, I'm going to apply some trig ratios to it. So if I do Fx over 60, that is my adjacent side over the hypotenuse, which is cosine of 30. If I multiply both sides by 60, I'll be able to find that my force in the x direction in this case would be 52 newtons. Conversely, in the y direction, if I do Fy over 60, that is my my opposite side over the hypotenuse, which is the sine 30 degrees. Again, we'll multiply both sides by 60 to find that the y component of this force is 30 newtons. Okay, and the whole reason that we do that for questions like this is to answer a question like the one on your screen. If the mass of the kid and sled is 62 kilograms and there is no friction, what is the acceleration of the sled? So here's an application of dynamics where, like before, we will draw a free body diagram. If we have a 62 kilogram kid and sled, that means that our gravity force acting on this thing would be 62 times 9.8 or 608 newtons. This time, we are going to have a normal force. And up to now, our normal force has equaled our force of gravity on a flat surface. That is not the case anymore if we have a force being applied at an angle. So instead of putting 60 newtons on this free body diagram, I'm going to break that force into its two components. The force that's pulling in the x direction is 52. The force that's pulling in the y direction is 30. Okay, so now if I go and I want to find the acceleration of this kid and sled, I'm going to get to a very important concept that we must remember whenever we are using vector analysis of physics problems. Okay, I've drawn little vector hats above the F and the A in our Newton's equation of F equals ma. So that represents both force and acceleration are vector quantities. So whenever you're using numbers in equations that are vector quantities, we have to make sure that those vectors are acting in the same direction. So in this case, our acceleration is acting in the x direction. So that means I only want the net force that is acting in the x direction. And in our case, it's just going to be 52 newtons. Okay, our mass is 62 times a, so we can solve for the acceleration of this thing as being 0.84 meters per second squared. Okay, so things change a little bit when we are pulling ropes at an angle. In this case, we're pulling a sled at an angle. Our normal force here, our normal force in this case no longer is the same as gravity. It's now going to be gravity less this force that is being applied upwards on this thing. So we'd have to subtract this 30 because these two forces here have to add together to give us, or to balance out, the force in the y direction, because we know that this thing isn't accelerating towards the center of the earth or accelerating upwards. So our normal force in this case would change, which in turn would change our friction for more complicated questions. Okay, so here's one application of using vector components to solve a physics problem. Okay, so this next case we'll look at, first of all, just resolving components into vectors when direction is given in a bit of a different way. So in this case, if we have a 20 Newton force that's acting 50 degrees north of west, I'm going to just keep that dotted line going and draw it with an arrow. That, in this case, our Fx is pointing to the left, our Fy is pointing upwards. So once we have a triangle here, we're going to go and apply some trigonometry to find our different values. Okay, if we do Fx over 20, that is adjacent over hypotenuse, which is equal to our cosine ratio. We multiply both sides by 20. We can find that our force in the x direction here is 12.8 newtons. Okay, similarly, if we do Fy over the hypotenuse of 20, that is opposite over hypotenuse, or the sine of not 30 degrees, 50 degrees. If we multiply both sides by 20, we can find that the force that's pulling in the y direction in this case is 15.3 newtons. Now, I'm just going to have a look at this and just do a little analysis because in this case, our Fx is pointing to the left. So I just want to be mindful that in this case, our force is acting to the left. So most times if forces are acting to the left or downwards, I'm going to include a negative sign there. Another way that you can talk about, in this case, a force that's acting toward the west or the left direction is just make sure that we indicate the direction on there. And this negative is going to be important when we start adding vectors using the component method, which is what we're going to talk about very shortly. Okay. Okay, so next, here are 3 examples that you can try. So for each example, if you could just draw a sketch, and in this case, my sketch for the first vector would be 21 degrees south of east. This vector is 52 newtons. And then I'm going to be asking you to find the x and the y components. So for each one of these vectors, you can set up a little table. If you could draw a little sketch for yourselves and then find what the x and y components would be for each one of these vectors. I'll take a little pause here. I encourage you to pause the video and try these out. Compare your answers with me when you're finished. Okay, folks, if you can check your answers with those. With the next question, I'll pause the video and see if you can tell me the answers to these in a little quiz format. Okay, so now that we can break vectors into their individual components, now we'll talk about how to add those things together. In our first lesson on vectors, we talked about adding vectors graphically or tip to tail. In this, the whole reason that we are finding the components of vectors is we are going to add them now using the component method, which gives us a little more accuracy and flexibility in how we find answers for more complicated questions. Okay, so here is a question where we are going to add two vectors together. We've got 12 meters at 30 degrees north of east plus 18 meters 40 degrees north of west. I'm going to skip back to my PhET vectors, and just by chance I happen to have two vectors here. My D vector is a vector that is drawn with a magnitude of 12 at an angle of 30 degrees. We have the X and the Y components there. Okay, with vector E, it just so happens to be a vector that is 18 meters long, that has an angle of 40 degrees north of west, or an angle, in this case with the PhET applet, of 140 degrees. And then we're given, of course, the X and the Y components. When we are adding vectors using components, we're really going to add up the X components and the Y components separately. Okay, so in this vector, this D, we're going to add the X component. We'll add the Y component, the X component of D, the X component of E. The result of those two things is going to give us the X component of our resultant. So if I click on the resultant here, if I click on the resultant and line it up as we do, where we start our resultant at the start and at the end. So if we add our X components of our individual vectors together, it's going to give us the X component of our resultant. Okay, similarly, if we do that with our Y components, we add the Y component of vector D, Y component of vector E. That is going to give us the Y component of our resultant. That is really what we are doing when we are adding vectors using the component method. Okay, now if I skip back to our window, I'm going to first of all just talk about those steps. So our steps for adding vectors with components. First, we're going to determine the X and Y components of each vector. Then we're going to add all the X's, add all the Y's. The totals of those X and Y components is going to give us the components of our resultant vector. Okay, then we'll use Pythagorean theorem. We'll find the size or the magnitude of our resultant. Okay, then we'll use a trig ratio, and we'll find the direction of the resultant. Okay, so here's that question again, and this time I'm going to include a handy table to keep things organized on my page. Okay, so our first vector, and I'm calling this vector number 1, and this is vector number 2. Okay, so for our first vector, the displacement in the X direction, and maybe I'll just draw a little diagram here just so we have a visual. We have 12 meters, that's 30 degrees north of east, and then 18 meters, 40 degrees north of west. Okay, so now I'm going to try and draw my vectors roughly to scale, but you see the diagram that I've done here, the quick sketch, 12 and 18, they don't have to be to scale, because I'm going to use math to figure out the different parts of those things. Okay, so in the first vector, if we look at the X and Y components, the X component of our first vector will be 12 times the cosine of 30. Okay, so that X component will be 10.392. The Y component of that first vector will be 12 times the sine of 30 degrees, which will be 6.0 meters. Okay, the second vector in the X direction will be 18 times the cosine of 40 degrees, okay, which is going to be 13.788. But then I need to look at this and realize, holy cow, my X component of this vector is pointing to the left. So I'm going to put a negative there, just knowing that that represents a vector that is heading to the west. If I draw the other part of that one, the Y component is pointing upwards. And that Y component is going to be 18 times the sine of 40, which is 11.57. Okay. Now, if I add all of the components, all of my X's up, I'm going to end up with an x, the x component of my resultant pointing to the left with a magnitude of 3.396. Okay, my y components of my vectors will add together to give us 17.57. Okay, and what we've just found now the x and y components of this resultant. So we can even just do a quick check here. Hey, the x component of our resultant is 3.4, y component is 17.6. Did we get that right? Sweet, we're good. Okay, next step is to then use those components of our resultant and go and find what the magnitude is going to be. Magnitude of our resultant. We'll use Pythagorean theorem to start. Okay, so r squared is equal to the other, or 17.5, 7 squared plus 3.396 squared. And I'll let you guys plug and chug that. We should be getting an answer of 18. Okay, our angle, here our angle within this triangle. I'm going to skip up to the top here, getting to find angle. So the tangent of that angle, theta, is going to be the opposite side, or 17.57, divided by the adjacent side, 3.396. Okay, I'm going to do the inverse tangent of both sides, and we should find that theta is 79 degrees. Okay, so to round this question out, state this answer fully with size and direction. This vector will be 18 meters at an angle of 79 degrees that is pointing north of west. Okay, and again, with this direction, you could state the direction as 11 degrees west of north, which would be totally accurate as well. Okay. Okay, next question. Can you please give this one a try and enter your answers into the boxes provided? Okay, so that wraps this small portion of vector components. If you could please go and try out questions 7, 8, 9, 10, 11, and 12 on your worksheet with a couple of caveats. These questions, 10, 11, 12, I'm going to make these optional. Questions 10 and 11, where you have initial velocity, acceleration, and time, you're going to be using this formula. And when you are using this formula, if you choose to try these out, because they are challenging questions, just remember that when you're using the formula on your screen, you have 3 vector quantities, so each of those quantities have to be acting in the same direction. Okay, question number 12, while optional, this is just a classic physics example, physics question. Please give it a try. Let me know if you have questions, and we'll see you the next time.